Hello. So the previous version of this lecture that I gave in fall of 2021 had some audio issues. I guess it wasn't recognizing my mic on the recording software. So I'm just doing a quick re-record of this. It might not have all the exact information that that original one had, but I think I have an idea of what was talked about in that lecture. So I'm going to try my best to cover all those things here, which means it might be a little bit shorter, but should hopefully cover all the same topics and not waste as much time talking about other things. So the two things that were covered in that video were Makefiles, at least a very baseline introduction to Makefiles, and then pointers, an introduction to pointers. I'm going to go into more detail about the Makefiles in this video than I originally did, but I just want to start out with a very brief introduction to them, what you need to know in order to be able to use them for the assignments in this class. So you can see here I have the Makefile open for the first assignment for spring 2022. And we could take a look at this and break it down and what it all means. But I think first let's just kind of get an idea of what a Makefile is before we try to dive into that. So you can see here I have an assignment from a previous semester that I wrote. And we have these source files, right? So we have a header file for a class called city, a header file for a class called stack, a source file called main.cpp, and then this is an executable, which I suppose I will remove for now just so we don't have to see it. So now it's gone. And then we have this Makefile. So what a Makefile does is it allows us to compile things and run some other commands and kind of make the compilation process for our program easier and faster. And this is especially helpful when we have really big programs. So let's just say if I wanted to compile this program, and I was doing it the way that you may have learned in CS 135, then what you might do is you might type G++, which is the name of our compiler, and then you might type the source files that you want to compile. In this case, just main.cpp is our only source file. And so we compile it, and you see if I ls, we have a.out, which is the executable that was made by this source file. And that's great. And so I could do other things, like I could do G++ and add some sort of parameters or flags. For instance, -o lets me change the name of the executable from a.out to something else. So maybe I say my executable, and then followed by the name of the thing I want to compile, and that works great, right? So we could do a bunch of different compiler commands, and not all the time are you going to want to compile just one thing, as we'll see when we get more and more files later in this class. And so a Makefile kind of helps with that. So the way you use a Makefile, it just has to be in the same directory that you're currently in, and then all you have to do is type the word make. I'll type the word make here, and you'll notice it does some extra things. It does some prints, which is what I actually have in this Makefile, and then you'll notice that it runs the G++ command. So it runs G++, does all these flags, it sets O to be Pathfinder, so the executable name is going to be Pathfinder, and then it compiles main.cpp. So by ls now, you'll see that we have a executable called Pathfinder, and that was made by the Makefile. So Makefile is just a collection of commands that you can use to actually just quickly compile without having to type out G++ and then all this stuff every single time. You just type the word make, and it does it. And it does do more than that, but at least for the sake of just getting an idea of why we would want to use it, that's what we're going to be using it for at the beginning of this class. So all you have to do is type make, and it will make all the things, assuming they're named correctly, that dictate what commands the Makefile has. Now I do want to take a quick look at both the Makefile for the first assignment of spring 2022 and then this one here. So you can see it printed a thing here. So it printed, what was it? Compiling city Pathfinder, and then it did the G++ command, and then it said done run Pathfinder, which was the name of the executable. And you can see that those three commands are right here. So I have @echo. Echo is just for printing, and then that string that I wanted to print to the terminal. And then I have the compiler command, which you notice is not written directly the way that it is there. And then I have another echo just to print something else. So it's really simple, just prints two things and does the compilation in between, assuming it succeeds and doesn't just error out. And then we have these macros up here. So this actually does kind of boil down to G++, all of those parameters, and then this part right here. The reason being is at the top of a Makefile, we're going to have macros, which are just essentially strings, or, well, yeah, we'll just say strings that will get filled in wherever you put the name of that macro. So we have here, for example, cc as a macro, and then $, parentheses cc, end parentheses, it will replace this cc, this whole thing, with the macro that's equal to. So this gets filled in G++, this gets filled in with all that stuff. You can kind of think of it like a global constant from actual programming languages. It allows you to quickly change things if you decide to rename something, or you want to add more dependencies to a bunch of different compilation targets, then we could do that. So let's take a look at this one specifically here that exists for assignment 1. So this one's even more simple. All it really does is compile. Now, when you do make, it's going to look at all of the available targets, and it's going to go for all first. You can actually target other targets as well, if you put make and then followed by the name of the thing that you want to target. So for instance, if I just put make main, it actually should just work the way that the other one did. But it will jump to wherever these labels are that have a colon after them. So for instance, here I could type in make all, or just make, which will do the all by default, or I could type make clean, which will do the cleaning part. It allows you to jump to a specific part of the Makefile if you just want that part to compile. So a Makefile is going to be made of a series of these targets, which are just names followed by a colon. It's a place to jump to, basically, when you compile the code. It'll compile everything underneath it that's not part of another label or target. And then it's followed by some dependencies and then any number of commands. So for instance, here, this has a dependency of Benford's law, which is another label. That means that when I do the compilation for everything, it's going to go and want to compile this Benford's law target. So it goes and does that. You can see that the Benford's law target has a dependency of Benford's law.o, which is this label. So when we go and do this command, it's going to go and do this one first. And then this one has a dependency of an actual file. So this one's not a target, right? There's no Benford's law.cpp here. It's just dependent on some sort of file. So this will recompile depending on this, which we'll talk about what that means in a moment. And then as far as this process goes, it's going to go and do this command. Again, this is going to get filled in because it's a macro. So this will do G++, all of these flags, C, Benford's law.cpp. And what this will do is it actually won't build the executable, but instead builds this .o file. And what a .o file is it's essentially like a compiled file. You can't necessarily run it, but it is all of your stuff compiled together. And then it simply does a link here on that. So it does G++, all of these flags, -o, executable, and then uses the object thing. So you don't have to always compile just a source, which is like C++ code. You can compile an object, which is like a precompiled sort of thing. It doesn't really affect this here, but it is useful in the future. So let's talk about why we have a file here, and then why we might compile to object files instead of vector. So imagine that you're writing a program where you have a class. Let's just say we're writing it in a file here called class.h, and then a corresponding class.cpp that implements all of the declarations here. It writes all the code for that, and then we have a main.cpp. So it's totally possible that we could have multiple CPP files, basically one that implements all the class code, and then one that does the actual main loop and utilizes some of that class code that we've written. Now, if we were to compile this all together, what it actually does is this generates all the code associated with this class.cpp when we run the compiler, and it would generate all the code associated with that. So they're in two different files, but they both need their code generated. One way we can kind of avoid just linking them together right away is we can compile them to what's called an O file. And an O file, or an object file, as the full name is just, it's the code compiled down somewhat so that the computer can understand it, but it has no knowledge of any other code that you've written. So what actually needs to happen when you do a compilation is it needs to link these things together. Basically, all that means is it needs to join these things into the same file and then resolve any pointers that it may share between two things. So basically, what happens when we actually do the compilation process is it mushes these things together and spits out an executable. Let's just say a.out. Now, we could just compile right away and put all the things there and have it automatically link these together and just mash them together, and that's fine. But the reason it gives us the option to do these separate, which is kind of what these Makefiles are doing, it's building a separate object file and then linking it into an executable, is that imagine we have hundreds of these. We're writing a huge program that does some really big application. Then if we were to compile every single time and just link everything together, then we end up having to recompile every single file that we've written every time we compile. So for instance here, if I wanted to recompile without separately making a file, then these are just going to have to compile class.cpp and class main.cpp, or sorry, file main.cpp, and compile them every single time I want to do some compilation. And that's not great, because if you have hundreds of thousands of lines of code, then that's going to be kind of slow and not always necessary. So let's say I go to compile these and I get a compiler error that says I forgot a semicolon in class.cpp. If I go and recompile everything, then I do need to recompile class.cpp because it had a typo in it, but I shouldn't go and recompile main.cpp because it was well written, we're going to assume. And so to avoid doing that, that's what a Makefile actually does, is if we use these targets, class.o and main.o, it actually checks, has the thing that depends on changed since the last time we compiled it? So if we go back and look at this, the reason why we have a benfordslaw.cpp is it's essentially asking, has benfordslaw.cpp changed since the last time we compiled? If it has, let's recompile it. And if not, let's leave it as is and keep the existing .o that we have and use that to link our thing. So it actually just keeps the old code, assuming that you haven't made any changes to it, and uses that to link. So it avoids recompiling code that you haven't changed since the last time you ran the Makefile. Now I know this can all seem a little technical at first, and there's a lot to handle, but I think the real takeaways of this are that in order to use a Makefile, all you have to do is type the word make, and that the purpose of a Makefile is to avoid recompiling a bunch of files over and over again, and also to avoid typing in a bunch of commands. If you have a whole lot of files and you need to update it, it allows you to kind of just quickly do that. So it's very useful, but those are the two main things that I want you to take away from this. Anyway, so that's kind of our introduction to Makefiles. Let's talk about pointers. So first things first, let's discuss a von Neumann architecture. A von Neumann architecture just describes the way we expect computers to be assembled. So we assume that a computer has a couple parts. It has a CPU, and then it has some form of I/O, input-output, like, for instance, a monitor, or a keyboard, or a printer, or a mouse. Then these are all examples of I/O because they interact with the computer, they provide input or output to the computer. So the input-output allows us to interact. The CPU is kind of like the brain. It does all the computation. It knows how to add and move and subtract and do math and all that kind of stuff. And then we have something like memory. So memory, we can have a couple different types. In most computers, there's really two levels. So there's main memory, which is something like RAM. And then you have secondary storage. Sorry, so I hit that. Secondary storage, which might be something like a hard drive. And they basically just store things. So they store data, programs, files, that kind of stuff. For the sake of this class, we're going to be talking about main memory, which is traditionally RAM. This is going to store where your program is. It's going to store all the variables in your program. It's going to store basically everything that's running on the computer goes there. Parts of loaded files go there. Secondary storage, we're not going to be too concerned with. This is usually like files that we're reading from a stream. When you have files that are really big, you don't want to load them all in main memory because it's generally smaller and more expensive, like money-wise. So you typically want to avoid putting way too much in main memory because it is a bit limited. So we put things like files that we don't access as often in secondary storage, and then in main storage is where most of our actual stuff goes. Okay. So the way we're going to understand memory for the sake of this course is kind of just like a straight line. And it's going to be filled with cells called bytes. So each of these is a byte. And then at each byte, we have an address. So similar to how you might index an array, these are just all going to have numbers that represent where they are. So I'm going to say this is hex 0, hex 1, hex 2, hex 3, hex 4. And then we keep going until we hit the very end of RAM, which would be, let's just say, in this example, hex F256, or 255, I guess. So it's really just a straight line that contains a bunch of these addresses, which is just a location. It tells you what number block is it in our list of blocks. Okay. So we have this. It's just this straight line that we throw things into. And when we've been writing variable declarations in any sort of previous assignment, what happens is that the variable needs to get put into some place in memory in order for it to be accessible. So for instance, I might make an integer x, and so what needs to happen is it needs to find a place to store it. Let's just say it goes here, and then it will put x with how many ever blocks it takes. In this case, I'm going to say 4 because it's an integer. And then now this space is designated to be where x belongs. These 4 boxes, these 4 bytes, are going to be filled with zeros and ones that represent what x is. And so we don't really have to manage that too much when we're in the CS135, but if we want to do some complicated things and kind of like efficiently use the memory that we have access to, then it's a good idea for us to be able to access this in some way and modify it ourselves. So let's say I do int x equals 3, and what happens is this box of 4 bytes gets given the number 3. So there's representation in binary of 3 right there. And let's say I want to be able to access that indirectly. And what we need is some sort of type that tells us how to access this thing. And so the type we have for that is called a pointer. The way we declare a pointer is we give the type that we want the thing to point to. In this case, we're just going to say it's going to point to an integer because x is an integer, followed by a star. So as many stars as you put is as many levels of pointers that you're going to have. In this case, we just want one pointer, which is going to be a pointer to x, we're going to say. And I'll just call this I pointer for integer pointer, and we'll just leave it there. So what this does is it makes a variable that is able to hold addresses. It's able to figure out where things are. Right? So what I'm going to do is, let's say I want to make it so that I pointer is able to point to where x is. But I might do something like this. So let's break down what this means. This is the variable x, and we have a new operator here. So there's an operator. There's 2 operators that deal with pointers, or 2 major ones. One is this one, which is, I would say, the address operator. This is the address operator. It gets the address of something. And then we're going to have another one that does the opposite. Uses an address to figure out where something is. So what this is going to do is it's going to say, hey, x, I want your address. And it will grab that address and store it into iPointer. So if we look back up here, the address of something is always going to be where it starts. So the address of x is going to be right here at position 1. Address 1 is going to be where iPointer ends up pointing. So this is going to resolve to hex 1, and it's going to be where x is located. Right? So just the thing to take away from this is that a pointer is a variable type that allows you to know where something is. What's its address in memory? Now, if we want to go the opposite direction, let's say we have an address and we want to be able to access its contents instead, then we have the opposite of this ampersand, which is going to be the dereference operator. So here I'm going to do a star I pointer equals 4. And what this dereference operator does is kind of like the opposite of what the address operator does. So if we consider what this address operator does, it took x, which was this box here, and it got where it's located, hex 1. The dereference operator goes to that address and treats it like a variable. It allows you to set the contents of that address as whatever type that pointer is. So here, because the pointer is an integer pointer, it's going to treat I pointer as an integer. So what this is actually going to do, it's going to go to where I pointer is. It's going to say, okay, there's an integer here, and it's going to overwrite its contents with what we're setting it to, which is the number 4. Now, because of this, I guess we should note here that this box was where x is. X is actually now 4. So you can see in our code, we never actually directly set x. After the 3 set, that is, right? We set it to be 3. But now that we have like an indirect reference to it, we've looked at its position and gone there and updated it. This will actually update the contents of x to be 4. So if I did cout x at this point, it would in fact print 4 and not 3. Okay, so pointers allow us to indirectly modify values, and we can keep multiple pointers to the same place and kind of update it as needed. So that's one thing we need to consider about pointers. Now this hopefully reminds you of something from CS 135, which is that whereas if I was to use normal integers, let's just say have int y equals x, and then do something like y equals 5, that after we do this, right, then by this line, we would expect x to be still 4 and y to be 5, right? We expect them to be different numbers. Even though I set y to be equal to x, we didn't expect it to overwrite the contents of x, right? Because we're not saying y is the variable x. It's not directly like math where there's like substitution or anything. We're saying set the contents of y to be the contents of x. Make y equal to 4, which is what x is. And then here, this wouldn't go and change x, right? It would just make y equal to 5. It's not going to change x even though it's equal to y. And so when we do normal variables with no pointers, it makes a copy of the thing, right? It copies the number 4 out of this x into our value y. But when we do pointers, it doesn't do a copy. It goes straight to the same location, and they're talking about the same memory space and therefore the same variable. And so they update the same space, the same memory. So when I actually update I pointer, which I set equal to the address of x, it does actually change x. So there's actually some key difference there between the way that this worked in what we're probably used to with just standard programming, where it makes a copy, versus now where it directly overwrites this. And so where you've used this before is probably something like this, where we write some sort of function, let's say void foo, and we do integer, let's just say n, and a second integer m. So remember, there were 2 ways to pass in variables to a function, which was pass by value and pass by reference. Pass by value was when you copy something, so that's similar to what we did in CS 135, where we just set variables here equal to each other. It copies their value from one to the other. And a pointer is a reference. So they're pretty much interchangeable words there, where we give the address of the thing, or in other words, we give the memory space to it, and it allows you to directly overwrite it. So that's actually what was happening with pass by value and pass by reference, is we were giving it a pointer to that location that was passed into the function, rather than just copying it over and making sure it was never modified. So it's kind of our our first fundamental difference between using pointers and what we're used to so far. Okay. So let's just talk about how we can use pointers to move around in memory and how they affect something like a class. So let's talk about classes first here. Again, let's say I have some sort of memory space. Again, just numbered 0 to whatever. And then I go and make a class declaration for a class called EX. And it takes an integer n and a character c. If you remember what we said about classes, is that they're kind of like a blueprint. They don't actually make anything. There's no instantiation done when you make a class, but it gives a description of how to make a new data type that can be defined by the compiler. So one thing I want to consider is that an integer is 4 bytes. It makes up 4 blocks of memory, and a character makes up 1. So if we kind of think this through, if I was to go and do a variable declaration for EX, what we want to consider is how this works in memory. And the way that this works is an EX type is going to take up 5 bytes. And the reason being is that 4 of them are going to come from this integer n, and 1 of them is going to come from the character c. When I do some sort of declaration here, it's going to say, okay, well, I know a class EX type takes up 5 blocks of memory, because that's how it's defined, or declared, I guess. And then the first 4 of those, I'm going to designate to be where n goes, and then the last byte here is where c goes. So it does, when you make a class, actually just put everything right next to each other in memory, and we can access it because of that. Or we have some sort of predictable thing about the way it's accessible because of that. One other thing to note is that it actually does tend to go in the order that you declare these things in. So n comes first here, it's the first 4 blocks, and then character c makes up the last block. If I flipped the order of these and wrote character c, then int n in that opposite order, then the first block would have been c, and the next 4 would have been the bytes for n. Okay, so the order does matter. It just puts them side by side until it fills up all the space. Okay. So one other thing we maybe want to consider is pointers with these. And then also we want to talk about how we can move through this in memory. So maybe the first thing to mention is we can use pointers with abstract data types like a class. So I could do EX that. When I do this, one thing I need to actually consider is the fact that it's not going to go and make this space. When I do a pointer, it actually is just saying, hey, I want an address to that thing. We don't know where it's located yet, actually. We have to figure that out later when we make the object. So this stuff, this n and the c, would not exist yet if I just made this a pointer. In order to do that, we actually have to construct the object. So we need to explicitly call a constructor in order for this to go and do that space. So I'm going to put this back. Let's actually do that. So the way we make new objects is using the new keyword. We can do this with a couple different things, arrays and objects in particular. And so the way we do it with an object is we simply give the word new, and then we give the constructor. In this case, I only have a default constructor, so I'm just going to call that, which is EX left, right. So what this does, it goes and does the constructor, and it makes a new object of that type, and then gives us back the pointer to it. Whenever you use the new keyword, it's always going to return a pointer. So what this does is it goes here, somewhere in memory, allocates the n, allocates the c, all right next to each other, and then when it's done, it gives us back a pointer to where this memory is. Okay. So one other thing we should note, that probably won't test on this, but just something to keep in mind, is you can actually go through memory space using pointers. So for instance, we have this generic type called, or not generic, I shouldn't say generic type. We have this general type called void pointer, which allows you to have a pointer with no specific type that it represents. Here, what we could do is maybe set void pointer, I'll say v pointer. We'll name the variable v pointer equal to e. And what this does is it's just a pointer. So let's say this address here was hex, let's say 0a, just pick a random number. And all it does is it stores where that pointer is. And we said that a pointer represents an address. And what a void pointer represents is it represents just the address, but it doesn't care about what's there. So as far as this knows, an integer could be there, a character could be there, there could be a float, there could be an object of some kind. It doesn't really know, it just knows where that thing is. And that's different than another kind of pointer because it has some knowledge about what is at that position. And so the difference between those two things is that if I was to do something like that dereference operator we talked about earlier that does star e, this goes and grabs an ex type at this place. So again, to remind what a dereference operator does is it goes to the place being pointed at, hex a, and it says, ah, there is an ex object there. I should go grab that. And so it allows you to use it like any other kind of variable or any other kind of object. It goes and grabs it, understands what that stuff means. But I can't do something like dereference the v pointer. When it's void, it only has a knowledge of the address, not of what's actually at that address. So when I do this, this is actually going to generate a compiler error because it's going to say, I can't dereference a void pointer. I don't know what it means for something to be void and like accessible. Right? So a void pointer is a little niche, but it just represents the address with no knowledge of what's there. What it does allow us to do, though, is kind of move through an object. So we can do arithmetic, addition and subtraction with pointers. So for instance, let's say I did v pointer equals v pointer plus 4. What this will do is it's going to go to the place that v pointer is pointing to, which is right here, and it's going to jump ahead by 4 blocks. So what this does is it goes 1, 2, 3, 4, and jumps to there instead. You don't necessarily have to do this with just a void pointer, but it's maybe just something to keep in mind. Now, in our example, we've moved v pointer up 4 spaces. So whereas it was pointing at the beginning of the object, which is where n was located before, now by moving it 4 forward, you can see where after n, we're now pointing to where c begins. Because of that, if I was to try to dereference it, doing a special way here, let's say I dereference after casting it to a character pointer, v pointer, then what this will do is it actually will print, so let's say I do c out here. This will allow us to access c and print it. So there's a lot going on here, but let's take a look. So we first have v pointer, which is again pointing to the beginning of c now. We've moved it 4 ahead in our memory. And then what we do is we cast it. So you can cast pointers if you want them to understand that what they're pointing it at is a different type than what you originally had. So here originally this was a void pointer. It had no knowledge of what's there. But now I'm going to tell it, hey, what you're pointing at, that's a character. This stuff here, it's going to be a character. And then after that fact, I can dereference it. So we consider that this expression, all it does is return the pointer as a character type, and then the next part here is going to then go grab the contents of that thing, since we said that's what this operator does, and go grab it. So this goes here, tells it, hey, that's a character you're pointing at, and then goes and grabs the character. This allows you to potentially treat data differently. This can be a bad thing because you might accidentally access things in the wrong way and you see just a bunch of garbage because it's interpreting it incorrectly. But it also allows us to do some strange memory stuff where we kind of just jump around and are able to see the contents of variables completely. So just as a note, we can do any sort of arithmetic, or we can do basic arithmetic with these pointers. So if you do addition, then it's going to go to the right in memory, it's going to go up, and if you do subtraction, it's going to go down. There's no multiplication, there's no division. You generally can't set this to be literals either. That's not a thing you can do. So I can't just set this equal to 5. It can't just go straight to 5 in memory because we can't really know what's there. So let's do a more detailed version of the pointer arithmetic. I want to do it with something that's not a void pointer really quick. So again, let's say we have some sort of memory. And then let's say, let's actually put more here. Free. And let's say I do, again, integer x. It allocates x to be right here. And then we do a integer pointer called iPointer that again equals where x is. So iPointer is pointing right here. And then let's say I do iPointer plus 1. So something important to consider when you do this arithmetic is it's actually based off of the type of the pointer that you're doing. So whereas in the last one it was a void pointer, which is just generically, it refers to addresses, when I added it, it always skipped one block at a time. If I do it with an integer pointer, for example, then it's not going to skip one at a time, but actually by one integer at a time, not one byte. So this integer x is 4 bytes right here, and that all makes up one single integer. When I do iPointer plus 1, it actually does not end up right here, which is one block or one byte after where iPointer is. It instead goes one integer forwards. So actually doing this iPointer plus 1 will end up right here. It goes all the way after one integer being x and skips that far in memory. So something to consider is depending on the type of pointer you're dealing with, the amount that it skips when you do arithmetic is going to change because it assumes you're talking about that type, and so it will allow us to skip forward. This becomes useful when we're doing arrays potentially, which we'll see in the future. But it might seem a little strange at first to do it this way, but that's just something to keep in mind. Okay, so that's just my basic overview of pointers. I do want to do one extra thing because I don't remember if I mentioned it in this part originally, which was just null pointers. So when we go and declare a variable, or any variable, but specifically a pointer type. So again, let's just do the same example here where I say integer x equals 3, and that goes into memory and puts x there, and then I do integer iPointer. By default, iPointer is not pointing anywhere. It's not pointing to x if I don't set it, right? But it's not going to necessarily have a value. So if you've used an undefined variable before in certain compilers, you may have noticed it just prints like random garbage, right? A pointer is no different. So by default, if you don't initialize a pointer, it's going to be pointing nowhere in particular. It's not going to be pointing to any specific object. If anything, it's just pointing to some random memory address which may or may not be in use. So for things like integers, we have a default value that we kind of expect, or that we might set it to if we're not planning on using it until later. So what I might do for something like x is set it equal to 0, because that's just like a fair value to set an integer to if I don't have any expectations for what it should equal. We have something like that for pointers as well. If you want a pointer to point to nowhere in particular, then that's called a null pointer. And this is just a constant. I think, in fact, it is just the number 0. And it points to nowhere in particular. This is just used as like a way to mark something to make sure that if you're not using it, or if you haven't used it yet, you have an idea that you haven't used it. So it's kind of just a default value that we can use to double check that we haven't used this pointer yet, or that it's not pointing into anything in particular. Maybe we used it and then decided that we don't want to point to that stuff anymore, and so this is a way for us to no longer look at it. Okay, so I think that's a fair overview of pointers. I think that's about everything that was originally covered, minus the program, I guess, but it would have done the same thing that all that text I wrote did anyways. So in the next video, I believe I do talk more in depth about pointers and dynamic memory allocation. If you feel like there's anything I missed, just since it has been a year since I've recorded this, and you end up having questions, just let me know. I can always do an addendum or something to this video.